I'm going to show you another way to be able to find the acceleration due to gravity on other planets as well, and go ahead and determine acceleration due to gravity on our own planet, Earth, as well. So how to find little g on other planets. Let's say we're standing on Earth, and yes, this picture is not to scale, but let's say we're standing on Earth. Here we are, and we're going to hold a ball 1 meter above Earth. Okay? Well, we know how to find the force due to gravity, or the weight of the ball on Earth, basically by using this equation, mass times gravity. And this equation works nicely for objects that are at the surface of a planet, but it doesn't always work nicely when objects are further away. So if we wanted to determine the acceleration due to gravity, g, let's say we didn't know it, of Earth. So let's start with this equation. Well, now we know another equation for force of gravity, the universal law of gravitation, which is Fg equals g_mm over r squared. R being the distance between the two objects' centers. And our two masses here would be mass of the ball and mass of Earth. Well, we know that these two quantities, force of gravity and force of gravity, they're going to be equivalent to one another. So if we set them equal to each other, we get Fg equals Fg, plug in our equations, mass of the ball times gravity equals gravitational constant, mass of the ball, mass of Earth, divided by r squared. We'll notice our mass of the ball cancels. We're left with g equals big G, our universal law of gravitation constant, mass of the Earth over r squared. So basically we can see that the gravitational constant only depends, or acceleration due to gravity only depends on the mass of the planet and the distance, in our case, the radius of the planet, plus the distance of the object above the planet. So you're going to need to use this table in your textbook to be able to solve some of these problems. Right now we're going to use the table, so it's page 223 in the textbook, in section 7.6. We're going to need the mass of Earth, and we're going to need the radius of Earth. Already given to us in our correct units, kilograms and meters. So mass of the Earth was 5.98 times 10 to the 24th kilograms. And our total R is going to be the total distance between the two objects from their centers, so their center of masses. So we're going to need the radius of Earth, and we're going to need the distance of the object above. Well, the radius of Earth is 6.38 times 10 to the 6 meters, and we notice the distance of the object above is 1 meter. But in reality, 1 meter is negligible to 6.38 times 10 to the 6th. If we were to add those two numbers together and put them into scientific notation, we would still get this number, 6.38 times 10 to the 6th. Okay, if we plug it into our equation, little g, acceleration due to gravity, is equal to our constant times our mass of Earth divided by our total radius squared. So 6.38 times 10 to the 6th plus 1, quantity squared. Meters cancels, kilograms cancel. Well, here meters squared cancels with meters squared. Here we have a kilogram cancel with one of our kilograms. We're left with a Newton over kilogram. We know that we need to be in units of meters per second squared. So let's do a little bit of unit analysis. A Newton over a kilogram. Well, a Newton is equal to a kilogram meter per second squared. That's where it was first derived, F equals ma. Now a Newton over kilogram would be a kilogram meter per second squared divided by another kilogram. Our kilograms cancel, leaving us with meters per second squared. So 9.8 meters per second squared. You could do this same setup for other planets as well, finding their acceleration due to gravity. So your turn. Find the acceleration due to gravity on Mercury. We know that it's 3.59 meters per second squared, but go ahead and use the table in your book on page 223 to prove it. Pause the video now and try this problem out, and then check your solution. Okay. Here's our solution. Our constant times mass of Mercury divided by the radius of Mercury squared. We're assuming we're holding a ball above Mercury, same setup as last time, and it's only a meter above, so the meter actually has a negligible impact on this great distance right here of our radius of Mercury. We get 3.59 meters per second squared.